Okay, so now we are going to consider this procedure of tree pruning. So this is something like regularization for linear models. So basically what we want to, if we have grown a very large and complex decision tree, we want to penalize it for being too large and too complex, and we are going to remove some part of it to make it simpler. And let me show you how this is done, right? So basically, if we have grown a tree, a large tree, something like what you see on your left, then after we have done it, so we can remove some parts, like this node, this node, this node, this node, this node, and these two nodes. And the remaining tree is actually the tree that you see on the right. Okay, now the procedure goes like this. So we first construct a large decision tree and let absolute value of t be the number of terminal nodes. Sorry. Now, decision tree makes its predictions by splitting the domain where our data lives into these decision regions, and the prediction for each decision region is just the average observed value of training data that belong to that decision region. So, and the decision tree, we choose these decision regions as to optimize the residual sum of squares, right? So given like this. Now, what we do now is we are going to first grow a decision tree that minimizes the residual sum of squares, but then we're going to, instead of minimizing the residual sum of squares, we're going to add this extra term plus alpha t, that is something like regularization term, right? So plus alpha times the number of terminal nodes. And now we're going to minimize this new loss function instead. Okay, so we will take a subtree that minimizes this new loss function. And this works like regularization for linear or logistic regression. And the optimal value of alpha is chosen by cross-validation. Right? So we split our data set into several so-called folds. We feed decision trees several times. So every time we remove one of the folds and feed the decision tree on the remaining data. And then we apply it to the remaining, the fold that was removed, and calculate the error on that fold. Right? So this is the cross-validation error. And this is what it looks like. Right? So we begin with growing a large decision tree, and then we start removing some parts. So like we removed some, removed some, removed some, removed some, removed some, for different values of alpha, right? So every time we choose another value of alpha, and for this new value of alpha, some part of the decision tree has to be removed as to minimize the new regularized loss function. And then finally, for a too large value of alpha, we are going to just end up with just one node. And that node just predicts that everything is going to be the average value of the training data. Okay, so the optimal value of alpha is chosen by cross-validation. So here is the plot. So depending on this value of alpha, and this CP here means alpha. And so this CP is actually alpha. So the vertical axis is cross-validation, and the horizontal axis is alpha. And what we see here is that as alpha increases, the number of nodes in our tree increases. So this is the size of the tree. So this is the number of terminal nodes. It increases, of course, and the cross-validation error, so basically it decreases, but it does not decrease monotonically. So here it grew a little bit, and here it did not change. So, but usually it's just that our data set is just too small, but usually it goes up and then it goes down and then up, and then we choose the optimal value of alpha here. So in this case, we could choose either this value or this value, but we prefer the final decision tree to be simpler, so which is why we choose this value. So this is the table. Cross-validation error is in this column. And again, so there are two observations with the same cross-validation error, and we choose the one that with a larger value of alpha, because then it leads to the smaller number of nodes in the decision tree. Okay, so this is how it works. Then we're going to use this optimal value of alpha to construct the final tree. But again, in R, it's just done automatically. So usually you don't really pick it manually. So maybe you will have to type one more comment to pick the optimal value, but that's it. It's very simple. So you don't really have to think too much about how to implement it, but you need to understand how it works, right? So, and this is a little quiz for this section.